In this video, we will talk about what Lorenz curves are. So let's begin with some background. So suppose that we have some resource. So there's some resource like income or food or land, maybe healthcare, let me write that better, healthcare that can be quantified. So we can measure it. So it can be quantified, and we want to describe how that resource is distributed. So how it's distributed across a population. Across a population. So for example, maybe we're talking about income being the resource, and the population that we're measuring it across is, for example, e.g., U.S. residents. Okay, so that is sort of our overarching question that we're going to try to examine in this section. So what we will do is we'll define a function called a Lorenz curve. So a Lorenz curve that does this, that will describe the distribution of that resource across the population. And then after we do that, after we have this function that does that, then we'll measure how equally or unequally, how equally/unequally the resource is distributed. So do a few individuals have a bunch of that resource while the bulk of the population has very little? That would be sort of an unequal distribution. So we will measure how equally or unequally it's distributed using the Gini index. And we'll talk about what that is in the next video. All right, so I want to introduce what a Lorenz curve is through an example. Okay, so let's look at an example. Okay, so in this example, I'm going to zoom it out a little bit so I can look at this better. The example says that the tables below, sorry, I should say summarize, not summarizes. The tables below summarize the net worth. A net worth, I'm going to measure that as their assets minus the debt. And it's measured in thousands of dollars of U.S. families. Okay, there were 77,418,000 families when this was measured. This is data from a census. And the convention I'm going to use, the convention that this data table uses is that if families have more debt than assets, their net worth is just going to count as $0. So if I look at this first table, that says census data, and the left column keeps track of the percentile range. So the way I would read this is, in this first row, the bottom sort of 25% of US families in terms of net worth have an average net worth of 0. And that means that they have just more debt than assets, or maybe an equal amount of debt than assets. Okay, and then the next row would say that the next sort of quarter of the population, so from the 25 percentile mark to the 50 percentile mark, their average net worth is 47.1, and then the K is a symbol I'm using to refer to thousands of dollars. Thousands of dollars. So we can see that as we go down this table, we're talking about families that earn more and more. So the bottommost row is talking about the top 10% of families in terms of net worth. Okay, so what about this table on the right? So the table on the right describes Lorenz data. So the way I read this graph is x, this variable, is a percentile variable. So an f of x represents the fraction of the resource that, let me zoom it out a little bit so I have some room to write. It's the fraction of the resource that the lowest x percentile of the population, so the bottom x percent of the population, has. So let's break down what this is really saying. So for example, so e.g., the fourth row of this Lorenz data table means, so in the fourth row, x is 0.75, and what that means is, it means the bottom 75%, because that's what I get if I convert 0.75 to a percent. I get 75%. And the percentile is talking about the people either at that threshold or below it. So the bottom 75% of US families had, and then the value on the right-hand side in the f of x column tells us what fraction of the resource that they held. So they had, so 0.139, which is as a percentage is 13.9%. They had 13.9% of, and I'm just going to say that this is wealth. I'm going to write wealth for short when we're talking about their net worth here. So if that seems like a pretty low number, a pretty low percentage of wealth for this big proportion of the population, it should. Income inequality in the US is a very real thing. So this is saying that the bottom three-fourths of US families are just have about 14% of the wealth. Okay, so I'm going to move this example, just this bottom part right here, to the top of the next page to give myself a little bit more room, and then write down a general description of a Lorenz curve. So, all right. Okay, so in general, if we have the point x comma f of x, so f of x is the y value, or the output, on a Lorenz curve, that means, it means the bottom x fraction, or I can think of that as a percentage by converting it to a percentage, the bottom x fraction of the population has fraction f of x of the resource, as we saw in that table right before this. So ultimately, to be able to do some calculus with this, we'd like to have a formula for our Lorenz curve. And it can be shown that a good approximation for these data points in that Lorenz data table is given by the function f of x equals 1 over 20 x plus 19 over 20 x to the 9. Okay, so I want to draw a picture of this, a rough picture of this, to give us a feel for what this would look like. Okay, and then after that I want to talk about some properties of Lorenz curves. So this is just one example of a Lorenz curve. Let's draw it. So let's draw some axes. And so in my axes, I'm going to have this be x, and the other axis represents y, or I can call it f of x. And in my data table, x sort of was limited to be between 0 and 1, and same thing for y. It was limited to be between values between 0 to 1. And it turns out with this function, if you plug 0 into it, that we get 0 out. So that is a point on the graph. And if you plug 1 into this for x, you'll get 1 out. So 1 comma 1 is also a point on that. And then roughly what the sketch looks like is it looks something like this. And it sharply curves upward like that. And I want to put some dashed lines here and some dashed lines here so I can see that this is sort of contained within this square where the side lengths are 1. And I'm also going to draw one extra curve in this. I'm also going to draw the diagonal line y equals x. Y equals x is called the curve of perfect equity. And I'll talk about why, but there's a connection between y equals x and the resource being perfectly equally distributed in the population. Okay, so what are some properties of Lorenz curves in general? So not just for this specific formula that I had in this example, but just in general. So one thing that's got to be true is that f of 0 needs to be 0. Because this is saying that the bottom 0% of the population has 0% of the resource, which makes sense, because if you're talking about 0% of the population, you're talking about no one. Alrighty, and on the flip side, f of 1, so that 1 inside the parentheses is talking about, if I convert it to a percentage, this would be 100%. This is talking about the bottom 100% of the population. How much of the resource does the bottom 100% have? Well, it has everything, because 100% of the population is everyone. So this output should be 1 to indicate that the 100% of the population has 100% of the resource. So other things that have to be true here is the domain and the range both describe percentages. The domain describes a percentage of the population, and the range describes a percentage of the resource. And percentages need to be between 0 and 100. So as decimals, they need to be between 0 and 1. So the domain and range are both the closed interval from 0 to 1. And we might be able to observe this just from the one example that we did, but it'll turn out that f, or Lorenz curve, will be increasing. And f can't go above y equals x, that curve of perfect equity at any point. And for this property, I want you to really think about why. This is something that we can understand conceptually, and I want you to think about why. What is it about what f measures that would make it be increasing and not have it be possible for it to go above y equals x? All right, so I want to make one note about this picture when we talked about this curve of perfect equity. So I'm just going to call it g of x. I'm going to call that function g of x equals x. G of x equals x is also a Lorenz curve. And this is perfectly equal. It's perfectly equal. For example, if we plugged in something like 0.3 into g, it would equal 0.3. And what is that saying? So the input of the function is talking about the bottom, whatever percentage of the population. So the 0.3 in the parentheses is talking about the bottom 30% of the population gets, and then the output, which is the other 0.3, tells us how much of the resource they get. So they get 30% of the resource. And that would be perfectly equitable. We would, if it was perfectly equal, we would expect the bottom 30% of the population to get exactly 30% of the resource. And that's true no matter what number I plug in to g of x equals x. And that makes it perfectly equal. So in our example, let me close that parentheses. Close that parentheses. So in our example, just by looking at the graph, the bottom 30% of, sorry, let me just say the bottom 30% has much less than 30% of the total income. And I can see that from my graph. If I were to look at the point where, say over here, where we have x is 0.3, the point on the graph above where 0.3 is on my Lorenz curve f of x, and then on the y equals x curve, it is way different for what that y value would be. Okay, so I want to end this video by stating what our goal is going to be to do now. Okay, so our goal is that we want, let me space this out actually, want a way to measure how equal or unequal a Lorenz distribution is. And this is what we're going to talk about in the next video. How do we measure this equal or unequalness? So in terms of our goals for this section, we have finished our first goal. We've introduced what Lorenz curves are and how they model distribution of some resource in a population.